You should be able to boil water, not by heating it, but by lowering pressure. And this is where I have a little demonstration. So here I have my liquid in a syringe. I have this kind of plugged off. And if I increase the volume, you know by Boyle's law, the pressure goes down, right? So let's, instead of heating it up, let's basically, oops, a little leak there. Let's see if I can turn this over and see if you can see it. Come on, it's worked before. Yeah. But if you look carefully, you can see more and more of these bubbles forming. Well, I'm getting that liquid to boil by decreasing pressure, believe it or not. And if I relieve the pressure, the boiling stops. There's one more time. Not as strong as I used to be. Yeah. But if you look carefully, you can see those boilers there. Yeah. You laugh. You try. But you get the idea. So again, with the phase diagram, that's what happens, okay? So also, if I were to decrease the temperature, you can get the melt to a solid, okay? So terms, you know these different terms, triple point, critical point, and basically, again, phase diagram, nothing more than just a mapping. You know, for a given substance, a given pressure, a given temperature, you can predict what phase you have based on the phase diagram. Now, you look at another phase, another material, you compare carbon dioxide. Carbon dioxide is nonpolar, right? It has only dispersion. Water has hydrogen bonding. So water has a lot more intermolecular attractive forces. Notice what kind of temperatures we have here. 0, 100 degrees C, 1 atmosphere. For carbon dioxide, we have, in order to have room temperature, you're going to have basically 1 atmosphere. You're going to have carbon dioxide over here, but it says that at room temperature and 1 atmosphere pressure, carbon dioxide is going to be a gas. Okay? But if you reduce the temperature, you know, to a point here, you can get it to solidify as a solid. And so if you look at normal dry ice, it's going to be kind of at a very low temperature, about minus 78.5 degrees C. Okay, it's going to be on this equilibrium line, which means the rate of sublimation equals the rate of condensation. Okay. Okay. So that's basically what I'm bringing out about phase diagrams. So again, the key points to realize about critical points, triple points, and how the different phase diagrams are. Another curiosity about the water phase diagram, notice that this line here, this is between basically solid and liquid. Notice that it kind of slants to the left as you go to higher pressures. And that's basically, which means if you have ice and you increase pressure, so you have ice at 0 degrees C at 1 atmosphere pressure, you're on this equilibrium point here. If you were to increase pressure of ice, you actually can get it to melt to a liquid. And that's because the ice, you give it its structure and so forth, in solid form, it forms crystals, and it actually has a larger density as a solid than it does as a liquid. So, based on what this phase diagram says, if you have ice at 0 degrees C, okay, you would be at equilibrium between liquid and solid. If you were to increase pressure, keep the temperature the same, you could actually melt ice by increasing pressure and keeping the temperature the same. And that has to do with the density of ice is actually larger than that of liquids. In fact, if you ever froze, ice in closed containers in the freezer, it splits open the containers. That's because the density of the ice is larger. Okay. So in the last few minutes here, so that's what phase diagrams are about. And liquid substances would have its phase diagrams, and it's all determined by those intermolecular attractive forces. Chapter 12, we're going to get into more next time.